Hello, and thank you for coming today. This morning it is my pleasure to introduce you to the AWS SDK for Go. My name is Michael Dowling, and I'm a software development engineer at Amazon Web Services, where I work on the SDKs and tools team. We're pretty excited about the innovative applications and services and tools that developers are using building with the Go programming language. It's simple syntax, strong typing, concurrency primitives, libraries. These things, they allow us to focus on the problem we're trying to solve instead of having to focus on the code. Since its launch, the Go programming language has had an enormous growth trajectory. And we've heard from more and more customers that you wanted an official AWS SDK for Go. I'm happy to say that we listened to that feedback, and we've since shipped an SDK to support the growing Go community and our growing number of Go customers. So we aren't quite done yet putting the finishing touches on the SDK, but we've come a really long way. So the SDK started out as the AWS Go project owned by Stripe, and it was coded in a way that's similar to our other SDKs. It was model-driven, it was easy to update, and it had a pretty consistent interface. So along with Stripe, we decided that the best thing to do for the Go community going forward was to have a single, canonical, officially supported SDK for Go. So AWS took over the project in January of 2015, and in June of 2015, after iterating on the project, adding new features and support for new services, we launched a developer preview. Now, since then, we've been incorporating customer feedback and adding new features, and we really appreciate that feedback because it's the thing that helps make all of our other SDKs great, and it's going to be what we use to help make the Go SDK great. So please keep that coming. So now I'll show you some links and resources that you can use when you're getting up and running with the SDK. And keep in mind that these slides will be posted after the conference, so you'll be able to download this and click through from there. So first up, no big surprise, the code is open source and it's available on GitHub. We use the issue tracker for things like feature requests and bugs, and we're always delighted when we receive a pull request from the community. Also available on GitHub is the Getting Started guide. And this is going to be your go-to resource when you're getting up and running. It shows you how to configure a client, credentials, configuration settings, and the basics of how to make a request. And the last resource I'll show you is the API documentation. So we host comprehensive API documentation for every one of our services that we support. And it includes the inputs and outputs of that service and all the operations. And my favorite thing about the API documentation is that for each operation, there's a little snippet of code that shows you how to format that operation, the input, and then also what the output format is going to look like. So that allows you at a glance to kind of get an idea of what the structure is of even some of our more complex shapes. Okay, so in the remainder of this session, we'll talk about how to get up and running with the SDK, how to build a simple Go application with the SDK, and at a higher level, we'll talk about how to deploy that application and scale it with AWS Elastic Beanstalk. But the first thing we're going to talk about is getting up and running. We'll talk about downloading the SDK, configuring it, giving it credentials, and then making a request. So just like other Go libraries, in order to get the SDK, you can use go get and passing in the SDK's import path. And those three dots, those tell the go get command to also download the dependencies of the SDK. Also, I should mention that we used tagged releases. And this allows you to track specific SDK versions and pin them to your local copy. Now, since we're still in developer preview, we recommend that you vendor the SDK into your application until you're able to pull in that update and test it out yourself. So the SDK is composed of two main sections under the root import path. There's AWS and service. So the AWS package, it's a collection of configuration and helper and utility tools that make using the SDK easier. So the configuration structs we'll talk about in this talk, those are in the AWS package. And next we have the service folder, which contains a number of client packages for each one of the clients that we support in the AWS SDK for Go. And you'll use these clients to make all of your API requests to our services. And in this example here, we're importing S3. but you could substitute this with things like DynamoDB or whatever client you're using. And within the client's package, you'll find all of the input and output structs associated with the operations of that client. Now that we know how to get the SDK, let's actually talk about how we can configure the SDK before we start making API calls. So the SDK requires two pieces of information before you can start using a client. It requires a region and credentials. A region is the geographic region that you're going to send your request to, and credentials are used to securely authenticate your request with our services. And the SDK has a default configuration struct that gets merged into the config struct that you provide to a client. And what this means to you is that you don't have to provide every single option when you're configuring a client, just the ones that diverge from the defaults. And the SDK, it also supports multiple unique service clients that each take their own copy of configuration. And this configuration is copied by value, which means that you can use these safely concurrently. So let's take a look at how the SDK can be configured with your credentials. The SDK has a few different ways for you to provide credentials, but the most important thing to keep in mind here is that you should never hard code your credentials in source code. And that's just because it's just too easy to accidentally leak those credentials. So let's say you accidentally push your credentials to GitHub. Suddenly, your credentials are in the eyes of people that they shouldn't know what your keys are, right? So now not only do you need to rotate your credentials, you also have to recompile your application and redeploy it. So we can avoid that problem altogether by never hard coding credentials. And in fact, the static credential provider in the SDK shouldn't really be used unless you're taking credentials from an external source and using those at runtime. Otherwise, there's several better options that you can use to get credentials into the SDK. And we'll cover those now. So first, if you don't supply credentials to a client, we'll use what's called a default credential provider. And this credential provider is just a series of credential providers, which are basically things that try to get credentials from a specific source. So we have a pre-configured series of these that try one after the other to resolve credentials in a known location and in a known order. So first off, if you don't provide credentials, the default credential provider will look at environment variables. It'll say, is the AWS access key ID and secret key environment variable defined? If it is, it'll use those, short circuit the rest of the chain, and those are your credentials. Now, if it can't find environment variable credentials, the next place we'll look is the shared credentials file. And this is basically an INI file that lives in your home directory, and it has a number of named profiles that you can use when configuring the SDK. So if you have a shared credentials file, and it has a default profile, then the SDK will use that and stop looking for more credentials. And finally, if the SDK still can't find credentials at this point, we will contact the EC2 instance profile credential server and ask it if it has credentials. And what this basically is you deploy IAM roles to your instances and give those instances specific capabilities that they can do and which resources they have access to. So in fact, this is the preferred method of deploying credentials to your applications if you're running on EC2. So I mentioned a shared credentials file. This is an INI file that lives in your home directory, and it is used by all of the AWS SDKs and tools, including the CLI. So if you use this file, you're going to get some really good reuse between all of our tools. And this file, it also has the added benefit of multiple named profiles, which are basically you give a name to a section of the INI file, and that can be associated with that name at runtime when you use it. So you can have like a dev and a production profile, for example. And if you specify the AWS_profile environment variable, the SDK will look for that profile when loading the shared credentials file. Here's an example of one. It's pretty simple. It's just an INI file with each section representing a profile. You can see we've got default and prod. And each one of these sections requires two keys, the access key ID, the AWS access key ID, and AWS secret access key. All right, now that we know how to configure the SDK, let's take a look at how we can actually create a service client and send an API request to a service. So in this example, we are going to create an Amazon S3 service client and upload a file to a bucket using a put object operation. At first, at the top, you can see we're importing the AWS package and the S3 service client. And in the main function, we are calling new on S3 to create our client. And notice that we didn't have to pass in any configuration settings. That's actually because we're relying on the default credential provider to resolve our credentials. And I said that we required a region, but here we specified that through an environment variable, AWS_region. So config is not required if you have all of your configuration set up through these things. So after you've created the client, you then call the putObject method on the client. And each API operation associated with a service has a corresponding method on a client of the same name. And those clients have a similarly named struct associated with them for their input struct and for their output struct. So putObject input is associated with putObject. When this calls and it successfully returns a value, you'll get a putObject output struct. And here we're passing in some of the values that are required for putObject input. This is the thing that uploads a file to S3. And we're providing a bucket, which is my bucket, a key, and a body. Now the body is an I/O reader, so that's good because you don't have to load all the data into memory up front. You can just stream it. And notice that we are using AWS string here. This is because throughout all of our services, we have a concept of an empty value. We need to be able to actually serialize an empty value, send that over a wire, and we need to be able to disambiguate between not being specified at all by a user. So in order to do that, we're utilizing pointers, which can point at nil values. And you know that you can't take the reference to a string literal without assigning it first to a variable. So AWS string just kind of wraps all that up for you nice and succinctly. It'll define the variable and return a reference to it. So it just makes it a little bit neater to use. Now, after you've sent this operation, you're sending your HTTP requests. The SDK does a lot more for you than just that. If an error occurs that can be retried, the SDK will retry that using exponential backoff. And there's a handler system that you can hook into at different lifecycle steps of sending requests to modify the behavior of the SDK at runtime. So there's a whole lot of really cool things that you can do with the SDK. All right, so now that we have an idea of how to get the SDK, how to use the SDK, and how to send a request, let's actually build an application with it. So the application we're going to build is a word frequency application, and it basically counts the top 10 most mentioned words in a file. It's a business critical application here. So we'll take a file, we'll upload it to an S3 bucket, and we'll process that file by counting the words in it. And once we've counted those words, we'll persist them to DynamoDB for long-term storage and send the resulting information of that result to a downstream SQS queue. And the goals of this application are we want to build something that takes advantage of Go's concurrency primitives and shows off how to use that with the SDK. We want to build something that's durable. So if a job fails while processing, we want that to be automatically retried without losing any information. And we want to build something that's scalable. We want to be able to keep throwing nodes at this and sustain heavier traffic. And also mentioning that this is on GitHub at this URL, so you can download this and look at the nitty-gritty details that kind of won't be mentioned in this talk. So here's a high-level overview of the architecture. So first we take a file on the top left, and we upload it to an Amazon S3 bucket. And then you can configure your S3 bucket to notify an SQS queue when a file is delivered to it. So we've set that up here, and it's pushing a message to an SQS queue. Then we have a word frequency service that is running, and it's pulling off of that queue, and then once it sees a message, it performs the actual work of streaming the data from S3 and counting the words, and then persisting the data to DynamoDB and sending a downstream message to an SQS queue. And what that SQS queue in the end allows is you can hook into that and react to when a file's been processed. So for example, you might want to delete the file from S3 because it's no longer needed. Or in our demo that we're about to show, we're actually going to use that to pull the SQS queue to know when our results are ready so that we can show them from the CLI. All right, so let's take a look at the client aspect of this application and look at actually utilizing the client. All right, so here I have, just to show that I've exported my region, AWS region, and I've got my access key ID and secret access keys exported. And we're going to run this command from our example project here. It's upload s3 main.go executable, and we will pass in the name of the bucket and the path of the file we're going to upload. So right now we're uploading the file to S3. S3 is getting the file, sending a message to SQS. SQS is being polled. We're counting the words and then persisting it, and there's our results. So we just did all of that, and our word frequency service persisted the data. We polled the SQS queue, and the top 10 most frequently mentioned words in that file are listed here. And there are a bunch of Latin words that I'm not going to try to pronounce. But this just shows that it works. And let's actually take a look at the code of this to see how it's done. So from our sample application, this is the main.go file. And this is the actual code of what we just saw. So first we do a bunch of imports, specifically mentioning here the AWS package, the S3 manager, which is a really cool abstraction we'll talk about in just a second, and the SQS service client. So in the main function, we're going to take the command line arguments, pretty standard stuff, validate them, and we're going to open a file, and we're going to use that as our body, the upload. And we're just going to stream this because it's an I/O reader. Now here, we're creating a new uploader, and this is an S3 upload manager that is similar to one of our S3 clients. Again, we don't have to provide configuration because it uses the same process of resolving your configuration data. And the reason we're using this is because we're not sure how big these files are going to be. What if someone wants to upload a file that's 20K? Well, that's pretty easy. We can just use a put object operation. But for an object that's 200 gigabytes, 200 terabytes, we want something better. And luckily, S3 offers a really nice feature called multi-part uploads. And that allows you to break a file into pieces and send those uploaded concurrently. And then once you're done, you say, hey, S3, I'm done. Can you put these back together for me and make them a single thing again? And that allows you to really quickly and easily upload a large file. And you can recover from errors by only having to upload any parts that may have failed, not the entire thing. So the upload manager here abstracts all that away for you. It looks and acts like a put object, but it'll pivot on whether or not to use a multi-part or a single put object operation based on the size of the input. So it's a really nice abstraction, and I encourage you to use it if you're not sure on the total size of your files. So we're calling the upload method, and it's got a similar structure: upload input, bucket, key, body. So if an error occurs, we'll exit out. Otherwise, we will wait for a result on the downstream SQS queue that we saw in our diagram. So let's take a look at how that works. So from the command line, we're sitting here, we're waiting for the result so we can report it to the user. And in order to do that, we're kicking off a loop, and we're calling receive message on SQS. And receive message is how you ask a queue, do you have any messages? And just like put object, we are putting in a receive message input, giving the URL of the queue we want to receive messages from, a visibility timeout, and a wait time in seconds. A visibility timeout allows you to tell SQS, hey, I'm going to try to do this work. If I can't finish it before the amount of time that I've given you in visibility timeout, consider it a failure and push it back into my queue so something else can retry it. So that's used for recovering from errors and things like that. And wait time in seconds tells SQS that if you don't have any messages for me right away, leave the socket open for this number of seconds, and let's just see if a message arrives. And this just makes it utilize less resources on your end and makes things work for polling and things like this. So that's long polling with SQS. And once we've received a message, we iterate over that because the receive message output struct has a messages field that is a list of messages. And we're going to parse those out and build up a job result struct. And we'll unmarshal that JSON data into a job result. And then we'll check, is this the actual message that we sent? Is this the same bucket and the same key that we're looking for? Because you need to do this because if someone else is also doing the exact same thing and they're trying to pull on their message, you want to make sure you're not interfering with them. So we look for our message. When we find it, we print out the result, and then we're going to delete the message from SQS just because it's no longer needed for our case. So that is the whole process of the client side of this application. It's just uploading a file to S3. We're pulling the SQS queue. And now let's take a look at the next part of our application. So our file is now being uploaded, and we have put the file into S3. S3 then sent a message to the SQS queue, which we can now start polling. And we'll talk about the word frequency service that we will deploy to Amazon Elastic Beanstalk. So here's our frequency service. It's made up of 3 main stages. There's the job message queue there at the top, the worker pool, and the result collector. And each of these stages are run as separate Go routines all at the same time. And they communicate with each other through channels. So our job message queue, it's going to be the thing that's polling SQS to look for new messages, which are files that have been delivered to our bucket. And it uses a visibility timeout to recover from error. And it will then parse the JSON data out of that message, extracting the object key in the bucket. And then it will build up a job and send that to the job channel. Now, our job message queue is then polled on by the worker pool. So it's a pool of workers waiting for jobs to arrive in the job channel. When a new job is available, the worker then pulls the job off the channel and streams the data from S3, counting the words in the file. And finally, when the result is complete, it sends the result data to the result channel. Then our result collector is polling on that channel, and it pulls the results off the channel, writing successful results to DynamoDB. If the status of the job is a failure, we're not going to delete the message from the originating SQS queue, but rather allow it to be retried. And we will always send a message to the downstream SQS queue. So let's take a look at each of these individual sections and look at the code on how they're implemented. So first up is the job message queue, and let's look at the code for that. So job message queue is in jobmessagequeue.go of our example project. And importing AWS, the SQS service client. And here's something interesting, SQS iFace. So all of our clients have interfaces that we define for them, which you can code to, and this allows you to more easily swap that out for mocking. So we encourage you to use that whenever you're integrating with the SDK. Then we have a job message queue struct, which has some fields that we're going to use, like the job channel we're going to be reading from, and the queue URL that we're going to read, and queue visibility. Let's take a look at the listen method. This is what's running in a Go routine. And the way this works is we set up a big for loop here, where we're just going to read from SQS using the receive message method. And let's take a look at that method. So receive message is defined here. We create a result of calling receive message on SQS, similar to what we just saw earlier, using a visibility timeout and wait time in seconds. And if we get our messages successfully, we'll return those messages to the wrapping method. So in this method, once we've got our messages, if we did not encounter an error, we will then parse each message and build up a job structure, and then send that job to the job channel so that our worker pool can then be made aware of it. So that's basically how the job message queue works. We're just reading off of SQS and populating the job channel. And next up, let's take a look at, no, that didn't do it. Let's take a look at the worker pool, which is the thing that is actually reading from the job channel and doing the work for us. So the worker pool code is defined in worker.go. This is also running in a Go routine. And we are importing S3 iFace here because we want to be able to mock that out easily. Worker pool is a struct that has n number of workers and a wait group. So here's the way you create a worker pool. We're going to first initialize the worker pool with our workers. And then for each one of our workers, we're going to add to the wait group. And we're going to then initialize the worker and then kick off the worker's run method in a Go routine. So n number of workers running in a Go routine. When the worker's finished its work, or the process exits, or the channel is closed, the worker's then going to check back in with the wait group and let it know that it's finished, decrementing the wait group count. So what that allows you to do is to basically block until all of your workers are checked back in so that you don't lose any work. And that makes it nice because you can then deploy updates to your application and not lose any of the work that you've been performing. So in this Go routine, in each one of these Go routines, our worker's run method is being run. So let's take a look at that. The run method of a worker is running concurrently with all the other workers. And we're going to do something similar to what we saw earlier. We have a big for loop that's running, and it's reading from the job channel. And when it gets a message, it's going to start building up a results struct, which has our job associated with it. Then we're going to process that job and build up our map of string of word to number of occurrences of that word in the file. So that's going to be done in the process job method. Let's take a look at that method. Process job calls get object on Amazon S3, passing in get object input, and that has a bucket and a key. And then we're going to get the body of that object, and that's going to be in an I/O reader again. And the way that we're going to count the top words is we're just going to stream the data from the I/O reader, counting the words, and only taking the top 10. Now, earlier I mentioned how we can upload massive files with multi-part upload. So what this means is that some of our files could be very small and very quick to process, while others might be really large. And a way that you can account for this with a visibility timeout is periodically update that visibility timeout as you're streaming the data. So we've implemented that in the count top words method. And you can check out that code on the example project on GitHub. Now, after we've processed the job and we've built up our word map, we check to see if there's an error. If there is, we set the status of the job to failure. We log that error. If it's successful, we'll associate the words that we got with that job, with the result, and then send the result to the results channel. So that's the worker pull. We're reading from the job channel and processing the file and sending the results to the result channel. And finally, let's look at the result collector. And this is a thing that's actually doing something with the data that we built up. So the result collector is defined in resultcollector.go, and it's fairly simple. We are going to run the process job result method, and this is similar to what we saw. It's a big for loop that's reading from the results channel, and we're going to take that result. If it's a successful result, we will then try to persist that result to Amazon DynamoDB. And in order to do that, we're using something called our result recorder here. And we'll talk about that in just a second. So if the result recorder fails to record to DynamoDB, we will mark the job as a failure and not delete the originating SQS message. So again, that allows us to recover from failure because SQS will resend that message into our queue. If it succeeded to record, we persisted the data successfully, so we know that we're done with our work. We then delete the message from SQS, and this prevents that job from being performed again. And finally, we then notify our downstream SQS queue, which allows things like our CLI to be notified whenever the job is complete. So the result collector is defined in resultcollector.go, and this uses a pretty cool abstraction as well. It uses the DynamoDB attribute package, and we'll talk about that. So here's the result collector record method. So first we're going to build up a result record stored in the record item variable, and this is just a simple struct, one that you might encounter in your applications where you have some fields that are, it's fairly simple. It's got a file name and then the map of the string to the number of occurrences. But we need to format this for DynamoDB. Its structure is slightly different than what you would probably utilize in your structs. It has basically the key is things like S, which is a string mapping to a string value, and B mapping to a Boolean. So the typing information is sort of in the struct. We actually have a really nice abstraction in the SDK called DynamoDB attribute, and that has a number of helper methods that allow you to convert your data into this type of structure. So the convert to map method is used here to take our struct and automatically marshal it into this attribute value structure. And this utilizes JSON serialization, so you can use struct tagging that you might be familiar with. And first we'll marshal it in the JSON, then unmarshal it to the attribute value structure. And one of the really nice things I want to point out about this abstraction is that it was completely driven and contributed to us by a member of our community in a pull request. So that's really awesome. It's contributions like that and interactions with our community that help to make our SDK really nice and easy to use. So that is awesome. And if you have any more contributions that you want to recommend, feel free to open up a pull request or just an issue and we can talk about it. So once we've marshaled the AV, the attribute value structs, we're then going to call put item on DynamoDB to persist that data. And we're going to build up a put item input, passing the table name, the attribute value that we just marshaled. And if it's successfully completed, we won't return anything. Failure, we'll let it know. So that's the result recorder. We're just persisting the data to DynamoDB using this nice abstraction, and our application is now working. We're polling and pulling from queues, and everything's working. So now we build our application. Let's take a look at how we can actually deploy it to Elastic Beanstalk. So the first thing we need to do is create an environment that we can deploy to and scale from. And once we've created the environment, we can then take a look at deploying it and scaling it. AWS provides a number of ways that you can get your applications into the AWS cloud. And today, we're going to be using Elastic Beanstalk to deploy our word frequency service application. And with Elastic Beanstalk, we can create our application's cloud environment. We can deploy updates and configure auto-scaling groups, all automatically through the console. So let's take a look at how we can create our environment and deploy to it. One other thing to mention, Beanstalk is also free of charge. You don't have to pay additional costs. You just pay for the AWS resources that you utilize. It's a really nice feature, and it's really easy to use. So we'll look at that now in the console. Now you can also use the EB tools from the CLI to set all this up, but we're going to be using the console today. And the first thing we need to do is at the top right hand of the corner, we need to create a new application. So let's do that now. Click on that, and we're going to give our application a name. So we'll call this Reinvent Demo 9000. We don't need to give it a description. So now you need to choose your environment. And there's a couple of options here. There's a worker and a web server. And the worker is used to pull messages off an SQS queue to perform work, and it's basically an abstraction that that Beanstalk provides. It sort of proxies through SQS to your instances. Now we could use this for application, but what we wanted to do was have more control over our queue so that we could control things like visibility timeout, and also to showcase some of the features of the SDK. So for this talk, we're going to be using a web server. And on our web server, we're going to choose the environment type. Now there's a number of environment types that may work for your application, and there's several that work for Go applications, including the pre-configured Go platform. There is a Docker Go platform and a generic Docker platform. Now the pre-configured Go platform is really easy to use because if you just follow a couple conventions, Beanstalk will automatically know how to use your application. And so we're going to use that today. And then we're going to make sure that our environment type is load balanced and auto scaled. So this makes sure that we have more than one instance deployed and that we can easily scale up and down based on load. So now we need to upload our application. And this is done by first cross-compiling your application to Linux so that it can run on Elastic Beanstalk. And then you need to zip that up, zip up the bin/application folder, which is used by Beanstalk, and then upload that to this dialog here. So I'm going to upload my own. And I've already done this because it's probably kind of boring to watch me compile and zip up a file. So I'm just going to upload that. This has the application we just took a look at. And then you can specify things like deployment limits. And this tells Beanstalk, hey, just upload to 30% of my instances at a time. If that succeeds, then continue to upload to the rest. And that allows you to deploy in stages. So we're going to just choose the default. Here's the environment information. And the important thing here is we want to make sure that our URL is available. So we want to make sure that the Reinvent Demo 9000 EMV is available. Let's check the availability. And it's green. That's good. Beanstalk also can also create resources on your behalf. So you can create an RDS instance that you can use with your deployment or run your deployment inside of a VPC. We're just going to skip this because we don't need this today. And next is configuration details. And there's a bunch of stuff you can configure here, like the instance type and EC2 key pair. I think those are the most important things that we're going to talk about here. So first up is the instance type. And this determines the processing power of the instances in your application. And you can choose from a number of types. If you're CPU bound, you might want to choose a higher CPU type. Memory bound, you might want to choose a memory instance. We're going to choose a T1 micro because we're cost conscious. And then we're going to choose a key pair. Now, you want to deploy a key pair to your instances so that you can SSH onto them and treat them just like normal instances. So we're going to use one that I've already created, EC2 test. There's a bunch of other options that you can check out later. And then we're going to click Next. You can tag your instances. We're going to just skip this for now. And permissions, those allow you to deploy an IAM role to your instances. And basically, you can specify exactly what those instances can do, the resources they can utilize. But Beanstalk will also create a default role for you. And this can be used when you're getting up and running. We're just going to go ahead and use that today. Use the default roles and call Next. So finally, here's the review screen. So once you've configured your application, you can make sure everything looks good. If you made any mistakes, you can fix that now by clicking on one of these links. Everything looks good to me. Then finally, you click Launch. And this is going to launch your instances. It's going to set up your load balancer, configure auto scaling, and your application is now running in the cloud. But this is going to take a little bit of time, and that would probably be boring to watch as well. So I've already set up a working deployment of this. It's actually the deployment that we contracted earlier from the CLI. So we know it works, and it's got this big green checkbox, so hopefully you get one of these too when you try this out. And this is kind of your at-a-glance dashboard of your environment. Everything looks good. You've got messages down here that you can look at whenever you're troubleshooting things. So the first thing you need to do after you deploy our sample application is set up environment variables that we can use from the actual application. So you click on configuration on the left here, and then we're going to go to software configuration. There's a number of things you can configure here, but I want to point out the environment properties. And these are going to be used in our application. So we need to tell it what queue you're going to be reading from, and the queue you're going to be writing to, and tell it the table name in DynamoDB to persist your results to. So all this is already configured. If you needed to change things, you could do that here. And then clicking Apply would then bounce your environment, restarting some instances, and updating them with the new configuration. So once you do that, your application's then running on Elastic Beanstalk. And people are uploading files, and they're really happy because they know the frequency of words in those files. But what happens if it catches on and like a ton of people hear about your awesome product and they want to start using it? Then you've got a scaling problem. But luckily, Elastic Beanstalk has really nice auto-scaling integration that you can use to automatically scale up and down based on load. So you go to Configuration, go to Scaling, and from here, you can specify things like auto-scaling settings. So we can say, I want to always run with at least one instance, or you might want to say, I want to have at least 10 at a time. And you can also set a cap, so never have more than 4 instances. You can specify other things like availability zones that you want to run in, and scaling triggers. This is what's interesting to our application. Now, because we're probably going to be CPU bound with building up all these maps and counting words, we're going to set our trigger to CPU utilization. There's a number of other scaling triggers that you can use, like network in and out, disk I/O type settings. We're using CPU utilization. And we're going to set it to be based on a percent, just to make it easier to understand what we're scaling on. And our upper threshold is going to be 75%. So if CPU exceeds 75%, we're going to start scaling up and fulfilling more traffic. Now, once the CPU then dips between our lower threshold, which is here, 25%, we'll start scaling back down because there's no need to have that capacity allocated anymore once your CPU dips back down to a reasonable level. And That allows you to scale up and down, saving money as your load increases and decreases. And you can also set up things like time-based scaling. If you know, like, typically your customers want to count words in a file at 3 p.m., you could set it up to do scaling based on that. And once you click apply, that will then bounce your environment and update your application. So that is the application. We created it, we deployed it. Today I've shown you how you can download the SDK, how you can start using the SDK. I've shown you how you can create a client and send requests. And we've highlighted how you can use a service client and Elastic Beanstalk to utilize some of Go's asynchronous programming model. And finally, we deployed our word frequency service to an application on an Elastic Beanstalk environment so that we can scale it up and down based on load. So I want to thank you very much for coming today. It's been my pleasure to demonstrate to you the AWS SDK for Go, and feedback is really important to us. Here's some ways that you can get in touch with us through GitHub, through the issue tracker. Send us issues, let us know what you think, pull requests. Those are really important to us. And these are also some links that you can use when you're getting started, including at the bottom there, again, is the sample application you can download. So thank you very much for your time.